Imagine you're standing at one end of a maze and you need to reach the other side. There are hundreds of ways to get there, but which one is the shortest? Now imagine you had to find that best path in a fraction of a second. That's exactly the problem A-Star was built to solve. And once you understand it, you'll start seeing it everywhere. So here's the situation. Between any starting point and any goal, there are countless possible routes. Some wander all over the place. A few are short and direct. What we really want is the cheapest path, the one that takes the fewest steps. But we don't want to waste time checking every single possibility. That would take forever. A-Star is clever because it explores only the routes that actually look promising and quietly ignores the rest. So how does it decide what looks promising? It gives every spot on the map a score, and the score comes from a beautifully simple idea. The total score of a spot equals the cost to get there, plus a smart guess of how far is left to go. Let's break that into two pieces. The first piece is the cost already traveled. That's the real, actual distance from the start to where we are right now. The second piece is the estimate. That's an educated guess of how much further it is to the goal. Add those two together and you get one number that answers the key question. How good is this spot overall? And here's the whole trick. A-Star always looks at the spot with the lowest total score first. Lowest cost so far plus best looking future, that's the one it explores next. Alright, let's make this real. Here's our map. It's a simple grid of squares. We've got one green square where we start, one square that's our goal, and a few dark squares that are walls we can't move through. We can step up, down, left, or right, and each step costs the same. Now for that smart guess, the estimate to the goal, we'll use something called Manhattan distance. Don't let the name scare you. It just means count how many squares across and how many squares up or down you'd need to reach the goal if there were nothing in the way. Simple as that. Now watch A-Star actually search. It starts at the green square and looks at its neighbors. For each one, it works out that score we just talked about and drops them into a group called the open set. Think of the open set as the frontier. All the spots we've discovered but haven't fully explored yet. Out of everything on the frontier, A-Star picks the one with the lowest score, steps into it, and expands its neighbors too. And notice what's happening. The frontier keeps stretching out toward the goal, not wasting effort wandering backward. Every spot it finishes with gets moved into a second group, the closed set. Once a spot is in the closed set, it's done. A-Star never goes back to it. Step by step, the search reaches toward the goal. And the moment it arrives, it stops, traces its steps back, and reveals the path. And there it is, the shortest route found without checking the whole map. Let's quickly talk about those two groups, because they're the heart of how this works. The open set is your frontier. Everything you've spotted but might still explore. Every time you pick from it, you take the most promising option. The closed set is everything you've already explored and locked in. You never revisit it, and that's exactly what stops A-Star from going in circles and keeps it fast. Now, everything depends on that guess we make, the estimate to the goal, and there's one golden rule. A good guess should never overestimate how far is left. When your guess never claims things are farther than they really are, we call it admissible, and A-Star is guaranteed to find the truly shortest path every single time. But if your guess is too greedy and overestimates the distance, A-Star might run faster. But it could miss the best route and hand you a path that isn't actually the shortest. So the quality of that estimate is everything. A better guess means fewer squares explored and a quicker answer. Believe it or not, that entire idea fits into just a few lines of logic. Start by putting the beginning spot into your frontier. Then, while there's still something to explore, take the spot with the lowest score. If it's the goal, you're done, trace the path and finish. Otherwise, look at each neighbor, and if you found a cheaper way to reach it, update its score and add it to the frontier. Keep the best cost you've seen so far for every spot and just repeat. That loop, running over and over, is all of A-Star. Now, is it expensive to run? It can be. In the very worst case, the amount of work grows quickly as the map branches out and the goal gets farther away. But here's the good news. In real life, A smart guess keeps A star focused and fast, so it almost never hits that worst case. The better your estimate, the less work it does. Let's weigh it up honestly. On the plus side, A star finds the shortest path when your guess plays fair and it explores far fewer spots and older methods that check everything blindly. It's also flexible. You steer its behavior just by changing that estimate. On the downside, its performance leans heavily on how good that guess is, and on very large maps, it can use up a lot of memory since it has to keep track of both the frontier and everything it's already explored. And this isn't just theory. A star is quietly running all around you. It's in the navigation apps that plan your route across a city, it's in video games, guiding characters smoothly around obstacles, it's inside robots finding their way through a room, and it even helps route data across networks. Anywhere something needs to find the best path, A star is often the brain behind it. So that's the whole idea. The total score equals the cost so far plus a smart guess to the goal. Cost behind you, estimate ahead of you. Balance perfectly to find the shortest path fast. If this made A star finally click for you, you know what to do. Thanks for watching Cool's Tech, and I'll see you in the next one.